Last time around we worked through our sum and difference identities for cosine. This time we're going to do sine and tangent. Still sum and difference identities in section 5.4, but we moved on to sine and tangent. Now, where do the identities come from? We don't derive these identities always, but we are going to do one of them. We are going to derive our sine sum identity. So we're going to start with things that we know are true, and we're going to figure out where this sine sum identity comes from. That's what it means to derive an identity. Well, I know that sine is the cofunction of cosine. So using my cofunction identities right here, using my cofunction identities, I know that the sine of theta, in this case, theta is being represented as a plus b. So a plus b is equal to theta. The sine of this angle theta, this sum, is equal to the cosine of the complement. So my cofunction, and now I need the complement of theta, 90 minus theta, which in this case is 90 minus that sum a plus b. Well, if I distribute here, I've got cosine of 90 minus a minus b. Just distribute that negative inside my parentheses, and then I can choose to group these two together so that I've got cosine of the difference of 90 minus a and b. So this is a cosine difference, where this is my first angle and b is my second angle. Alright, cosine difference. Cosine of the first angle, cosine of the second, plus sine of the first angle, sine of the second. Well, now I can use my cofunction again. Cofunction of 90 minus a is the same thing as sine a. Sine of 90 minus a is the same thing as cosine a. And this is our sine sum identity that we have derived. So by using things that we already know, identities that we're already comfortable with, that's how we get from here to there. We showed how to derive that. Now, you're not going to have to prove to me how to derive these identities, but it's good to start thinking conceptually. That's the same type of process that we use with verifying identities. Notice that sine sum matches algebraic sine, plus and plus. Sine difference is going to match that algebraic sign. Minus goes with minus. But this time, the pattern is sine of the first, cosine second, and then the next product is cosine of the first angle, sine of the second. Those patterns you need to get familiar with so that you can recognize them, so you can find the identity when you need to use it. Remember, you don't have to memorize all of the identities because you will have access to your identity sheet on test 3, 4, and the final. We're not going to take the time to derive our tangent sum and difference identities. They are quotients. So we have this big rational expression over here for tangent sum and tangent difference. Tangent sum has the sum of the two tangents of the angles in the numerator, and then 1 minus the product of the tangents in the denominator. Tangent difference has the difference of the tangents of the two angles in the numerator, and then I've got the sum, 1 plus the sum of the product in the denominator. So my tangent sum and tangent difference are identical except for where those algebraic signs fall. Okay, so let's use some of these to find exact values. Anytime you're told to find exact values, you know you can't just pull out your calculator. This is not a special angle, this is not a special angle. So I'm going to have to use something else to get that exact value. I need to use the special angles so that I have exact values that I know that I can plug in. Now we did this with section 5.4 and, or excuse me, 5.3 in our cosine sum and difference, so we're going to do the same process with our sine and tangent sum and difference. Negative 15 degrees or positive 15 degrees, not a special angle. But I can think of a negative 15 degrees as well, you know, that's the same thing as 30 minus 45 degrees. 30 degrees minus 45 degrees, degree symbol is crucial here. That difference is negative 15 degrees. These are both special angles. So I can use my sine difference identity to figure out the exact value. Sine difference identity, sine of the first angle, cosine of the second, minus cosine of the first angle, sine of the second. 30 and 45 degrees are both in quadrant 1. 45, super simple there, square root 2 over 2 for cosine and sine. For 30 degrees, cosine is larger than sine. Everything is positive. Plug in all 4 of those values because I know all 4 of those values. So this one is, nope, not square root 3 over 2. Sorry, that's my sine function value, not my cosine. How about a 1/2 times square root 2 over 2 minus square root 3 over 2 times square root 2 over 2. These values are still going to look very similar because I'm just using the same 3 basic coordinates. 1/2, square root 3 over 2, and square root 2 over 2. Notice I've got the same denominator in both of those terms, so I can write it as a single term, as a single rational expression. Over here, tangent, we can use tangent sum or tangent difference. I need special angles. We talked about this with our cosine sum and difference identities. Our special angles and radians, all of our denominators are factors of 12. 12 is a multiple of each of those. So I need to figure out what I can add together to get 13 that's going to give me special angles, something that's going to reduce to special angles. We're just going to go with what I've already set up. 10 and 3 is 13, and both of those will reduce to special angles. So 10 pi 12ths plus 3 pi 12ths gives me my 13 pi 12ths that I need, not a special angle. These two, however, will reduce to special angles. So 10 pi 12ths is the same thing as 5 pi 6ths. 3 pi 12ths is the same thing as pi 4th. And I can use this tangent sum identity with these special angles to get the value of tangent of 13 pi 12ths. All right, tangent sum identity right here. Tangent of the first angle plus tangent of the second angle all over 1 minus the product of those tangents. Well, what are the tangent of these angles? Tangent of pi 4th is easy. It's just going to be 1. But tangent of 5 pi 6th. Well, let's look at this. 5 pi 6th is over here, right here. Tangent is going to be sine over cosine. So it ends up being 1 over negative square root 3 because those 2's are going to cancel out. If you need to see that, tangent of 5 pi 6 is positive 1/2. Good grief. Got my negative in the wrong spot. Positive 1/2 over a negative square root 3 over 2. Remember that we said that those denominators would cancel because when you multiply by the reciprocal, this would be 1/2 times negative 2 over square root 3. Cancels, and I get a negative 1 over square root 3, and I have to rationalize. So this tangent of 5 pi 6 becomes a negative square root 3 over 3 plus tangent of pi 4th is just 1. My denominator, I have 1 minus, and then I have the product of those two, so negative square root 3 over 3 times 1. All right, so in my numerator, let's turn this around and make it a little neater. 1 minus square root 3 over 3. In my denominator, I have 1 plus square root 3 over 3. Sorry, I bumped things and made them wiggle. Now, this is ugly. It's kind of a mess. I'm going to start by clearing out those little internal denominators by multiplying by well-chosen 1, 3 over 3. When I distribute that 3 into my numerator, I get 3 minus square root 3. When I distribute it into my denominator, I get 3 plus square root 3. Now, I don't remember if we have rationalized with two terms in your denominator that you have to rationalize or not. When you have to rationalize with two terms, you multiply by the conjugate over itself. So the conjugate of my denominator here would be 3 minus square root 3. Multiplying by that well-chosen 1, anything over itself is 1. I'm using my well-chosen 1 as the conjugate of the denominator. I'm going to FOIL. I'm almost out of space, so let me get some blank paper here so that when we FOIL we can see what happens. When I FOIL, my numerator, I've got 3 times 3 is 9. My outside product is a negative 3 square root 3. My inside product is a negative 3 square root 3. My last product, a negative times a negative, is positive. Square root 3 times square root 3. Square root 3 squared is just 3. So that's my numerator. In my denominator, 3 times 3 is 9. Outside product and inside product are opposites. Negative 3 square root 3, positive 3 square root 3. They're going to add to 0. That's why we chose to do it this way, so that that would add to 0. And then I have a positive times a negative. Square root 3 times square root 3 is just 3. When I clean up that numerator, 9 and 3 is 12 minus 6 square roots of 3 all over 6. And that will simplify. I can think of factoring a 6 out of my numerator and then canceling, or I could split it apart and say that's 12 over 6 minus 6 square root 3 over 6. Either way, that simplifies to give me 2 minus the square root of 3. 2 minus square root 3. Okay, if you got lost in that, I strongly recommend that you take a minute and you work back through it. You pause the video, you go back, you do it step by step until you get comfortable with those algebraic operations. Okay, so for this one, I have the other side of my identity. Let me kind of divide this up a little bit so that we can see we've got some space. So for this one, I've got the right side of an identity, and I know it's going to be a tangent identity because that's all I've got. So when I look at my tangent identities here, I've got subtraction in my numerator, addition in my denominator. That's this one. That's tangent difference. So tangent of A minus B. So this is tangent difference, tangent of A minus B, so 100 minus 70 degrees is tangent of 30 degrees. Now, 30 degrees is a special angle, so I can use my unit circle and figure out, okay, tangent sine over cosine, 30 degrees is in quadrant 1, so they're both positive. So we end up with a positive square root 3 over 3 as our tangent function value. For D, sine of 75 degrees, I want an exact value. 75 is not a special angle, so I've got to do something else. 75 is the same thing as 45 plus 30 degrees, and that's sine sum. Using my sine sum identity, keeping angles in the order I need them to be in. Everything is in quadrant 1, so everything's positive. And then I take that last step to write it as a single rational expression. All right, we're going to do a couple more. Let's do F really quickly because it's using the right side. This one is super simple. I want to say, okay, this is the right side of one of my identities. I've got sine, cosine, cosine, sine. So that's going to be one of my sine identities. I'm subtracting here, so that's sine difference. So that is A and B. So that is sine of A minus B, which is the same thing here, 40 minus 160, both in degrees. That is a sine of a negative 120 degrees. You know what? We can use our even-odd identities here. Even-odd identities. Is sine even or is sine odd? Well, fundamental identities, sine is odd. So a sine of a negative 120 is the same thing as the opposite of sine of 120 degrees. 120 is in quadrant 2. Sine is positive here. So the opposite of that is a negative square root 3 over 2. So we went all the way to a value. Okay. Going back up, this is the one we're going to have to do a little bit of work on. Tangent of 7 pi 12ths. I am going to say, okay, well, 7 is 3 plus 4. So tangent of 7 pi 12ths is 3 pi 12ths plus 4 pi 12ths, and those are going to reduce so that I've got pi 4th and pi 3rd, both angles in quadrant 1, so they're both going to have positive function values. Tangent sum identity tells me I've got tangent of the first plus tangent of the second angle over 1 minus the product of those tangents. The tangent of pi 4th is 1. Anything over itself is 1, plus tangent at pi 3rd ends up being square root 3 over 2 over 1/2, so it's just square root 3. 1 minus, and then 1 times square root 3 is just square root 3. And we kind of cut to the chase. We cut out some of those harder steps, and we got straight to the part where we need to rationalize our denominator with 2 terms. Remember, you rationalize a denominator of 2 terms by using the conjugate of that denominator as your well-chosen one. There's my conjugate, well-chosen one. When I FOIL, my numerator becomes 1 plus square root 3 plus square root 3, that's 2 square roots of 3. Square root 3 times square root 3, square root 3 squared is just 3. In my denominator, 1 times 1, outside and inside products are opposite, so they add to 0, minus 3, because square root 3 squared. So I've got 4 plus 2 square roots of 3 over a negative 2, and I need to simplify. 4 over a negative 2 minus 2 square root 3 over 2, or plus a negative 2 here. Either way, my signs, I'm going to end up with a negative 2 minus square root 3 as my exact value for tangent of 7 pi 12ths. All right, excellent. Okay, so for this next one, we're going to write each function as an expression involving functions of theta. Anytime you're given a setup like this, fill in everything you know. That's kind of your rule of thumb. You're going to fill in everything you know. Identifying, I've got sum identities and a difference identity here. Referencing your identity sheets for sine and tangent, or you can pull out your big identity sheet where you've got sine and tangent, sum and difference right here together. This is going to be sine sum, first angle, cosine second angle, cosine of the first angle, sine of the second angle. Well, theta could be anything, but sine and cosine of 120, we know those from our unit circle. 120 is in quadrant 2, so sine is positive, but cosine is negative. The only further thing I can do, this would be square root 3 cosine theta over 2 minus sine theta over 2. I can write that as a single rational expression with a denominator of 2. For the second one, tangent sum. Well, 3 pi is a special angle. This is 2 pi. 3 pi is right over here. This is 3 pi is coterminal with 3 pi. So that's my cosine and sine function values. So tangent theta could be anything, but tangent 3 pi is just 0 because it's 0 over negative 1. Anything times 0 is 0, so that product here becomes 0. 1 minus tangent theta times 0, that's just 1 minus 0 is 1, right? So I have tangent theta over 1, or just tangent theta. And here I have sine difference. Sine theta, cosine 270 minus cosine theta sine of 270. 270 is one of my quadrantals. It's the same thing as 3 pi halves. So I plug in what I know. Sine theta times 0 minus cosine theta times negative 1. Well, anything times 0 is 0. Negative and a negative is a positive. So I've got positive cosine theta there. Okay. Now I failed to shorten this like I thought I had, so I left in 3 more examples that I didn't really intend to leave in. It just kind of happened. So what I'm going to do is I'm just going to give you the answers for these 3. When you work through these sum and difference identities for sine and tangent, filling in what you know, this is what you should get for D. Notice that you have to be very careful that this radical does not extend over my sine theta. Sine theta should not be underneath that square root 3. There's E. And then F should simplify to sine theta. So I want to encourage you to work through those on your own. Make sure that you understand what you're doing, and then we are going to move on to figuring out A plus B. Now, we are going to be using, we need to be paying attention to what quadrant we're going to be in. Okay? Suppose that A and B are angles in standard position, where we're given cosine of A. So this is my information about angle A. If A is between pi and 3 pi halves, then I know that A is in quadrant 3. And then I'm given B, information about angle B, and B is between 3 pi halves and 2 pi, so B is in quadrant 4. So let's sketch those. A is in quadrant 3. This is going to throw me if I do A on the left and B on the right. Nah, we can do it. We can do A is in quadrant 3. I'm given cosine as a negative 7 over 25, so I need my y value, which is also going to be negative. B is in quadrant 4. I'm given sine is a negative 3 over 5, so I need x, and x is going to be positive. Alright, so for angle A, I know that x is negative 7. I need to figure out y, and I know that r is 25 for angle A. Well, how do I figure out y? Well, x squared plus y squared equals r squared, my Pythagorean theorem. If I'm solving for y, I'm subtracting that x squared. So y equals square root of r squared minus x squared. So 25 squared minus 49. And y is going to be negative because of the quadrant that I'm in. So I get negative square root 625 minus 49, which gives me a negative 24 for y. And then I've got b set up so that x is what we need to figure out, y is negative 3, and r is 5. Working out the same process, x is going to be positive because I'm in quadrant 4. 5 squared minus negative 3 squared. So 25 minus 9 is square root 16. So x comes out to be 4 for angle B. Now I've got these a little bit out of order, so we're going to have to pay attention down here as we work through these. We've got all 3 of these. Let's start here. Sine of A minus B. So sine difference identity. Let's start by saying sine A cosine B minus cosine A sine B. Well, sine of A is over here. Sine of A is negative 24 over 25. Cosine B, cosine is 4 over 5 minus cosine A, that was given to us, negative 7/25. Sine B was given to us as negative 3/5. So a negative and a positive is a negative, so that's a negative 96 1/25 minus, and then a negative times a negative is a positive 21 1/25. Negative 96 and negative 21 is a negative 117 1/25. So that's the sine of those, the difference of those two angles. Now let's figure out tangent. So tangent, using my tangent difference identity, tangent of the first angle minus tangent of the second, tangent A minus tangent B over 1 plus the product of those tangents. I'm going to give ourselves plenty of space for this one. Tangent A. Tangent is sine over cosine. So when I'm looking at sine and cosine of A, sine over cosine, those 25s are going to cancel out, right? So I get a negative 24 over a negative 7, which is a positive 24/7. You can also think of it as tangent is y over x. So for angle A, y over x. Minus tangent of angle B, y over x, is a negative 3/4. So that becomes a plus 1 plus, and then I have to find the product of those two tangents. So this becomes 24/7 plus 3/4 over 1 minus 24 times 3 comes out to be 72, and then 4 times 7 is 28. Now I'm going to have to clean this up, so I need common denominators everywhere. This is going to need to be times 4 over 4, times 7 over 7, and times 28 over 28. So when I rewrite that down here, now it looks like 4 times 24 is 96/28 plus 21/28 over 28/28 minus 72/28, which gives me 117/28 over a negative 44. Yep, negative 44/28. Those 28s are going to cancel. So I have negative 117 over 44 as my tangent difference. Now we got to figure out what quadrant they're in. Well, not they. What quadrant this this angle is in, a minus b. Quadrant of a minus b. Well, what do we know? We know that the sine of a minus b is negative, and we know that the tangent of a minus b is negative. So where does that happen? Sine is negative down here in quadrants 3 and 4. Tangent is negative where we've got 1 plus 1 minus in the x and y, so it's negative in quadrants 2 and 4, which means that a minus b must be in quadrant 4 because that's the only quadrant where both of those things are true. Okay, so algebraically intense, right? We're using a lot of algebra, order of operations, keeping track of your algebraic sign, positive or negative. We have one more example of that. I meant to take that second example out. So instead of taking it out, I'm going to give you answers. I encourage you to work through it on your own and make sure that you get the same thing that I get. For sine of the angle sum, you should get 16/65, not 25ths. Let me fix that. What happens when I have it worked already to the side and I just look and glance too quickly? I get tangent as 16/63. Both of those are positive, so you're looking for the quadrant where both sine and tangent are positive. Sine is positive here, tangent is positive here and here, which means we are in quadrant 1 for a plus b. So make sure that you check yourself and can do the algebra necessary to come up with those values for sine and tangent sum of a and b. Angle A will be in quadrant 2 because it's between pi half and pi. Angle B will be in quadrant 3 because it's in pi and between pi and 3 pi halves. Alright, last step, last example on this section. We're going to do a couple of verifications of identities. We're going to be using our tangent sum and tangent difference identities. Now remember, the goal is to start with the more complex side typically, and then it's easier to simplify that way. So I'm definitely going to be starting over here on the left. I've got a tangent sum and I've got a tangent difference. I'm already kind of thinking ahead and going, you know what? Pi 4th is a special angle. I'm going to be able to plug values in for pi 4th. So let's just set up both of these identities. So we've got tangent pi 4th plus tangent t is my argument over 1 minus that product. And then I'm going to add to that the tangent difference. So tangent pi fourth minus tangent t, 1 plus that product. Okay, so what's the tangent of pi fourth? Well, tangent at pi fourth is just 1. So since tangent at pi fourth is just 1, that means I have 1 plus tangent t over 1 minus tangent t plus 1 minus tangent t over 1 plus tangent t. Now as I look over here, I don't know what I got going on in the secant square up here in my numerator, but I see I've got difference of squares in my denominator, and I've got conjugate pairs as my denominators here. So I can make that happen for sure by multiplying and finding a common denominator. If I take this first and multiply by 1 plus tangent t over itself, and I take the second one and multiply by 1 minus tangent t over itself, I get my common denominator difference of squares, 1 minus tangent squared t. So let's go ahead and set that up, 1 minus tangent square t, and that's my denominator. So we are in really good shape here. So let's FOIL out these numerators and see what we get. Here, FOIL 1 times 1 is 1, plus tangent t is plus 2 tangent t, and then tangent t times tangent t is plus tangent squared t. Now for this one, same thing, only I've got negatives here. 1 times 1 is 1, so plus 1. Negative is minus 2 tangent t, and then plus tangent squared t. Alright, so let's clean up that numerator. 1 minus tangent squared t is my denominator. Let's look and see what we've got in our numerator. 1 and 1 is 2. 2 tangent t and minus 2 tangent t, those are going to add to 0. And then I've got plus 2 tangent squared t. Well, I've got 2 plus 2 tangent squared t. I've got 2 secant squared t. Tangent square and secant square, that rings a bell as a Pythagorean identity. Tangent square plus 1 equals secant square theta. So if I just factor out that 2, I have 1 plus tangent square theta, t, not theta, switched my arguments, over 1 minus tangent square t, and 1 plus tangent square theta, tangent squared t, 1 plus tangent squared t is secant squared t. So that numerator is 2 times secant squared t, and that's what I was looking for. And that still needs to be a t. I said t and I wrote theta. Alright, so that one verified. Using a lot of algebra, using that FOIL technique. I've got a sine sum and a cosine sum identity. These are both special angles, so I know I'm going to plug in values that I know here. I'm going to start with this that is the left side. I'm going to start with this left side. Sine sum, cosine sum. And then I'm going to add to that, so that's my sine sum identity. Then I've got cosine sum. That's that second identity. And then I'm going to plug in the things that I know. Well, I know that sine at pi 6 is 1/2. I know that cosine at pi 6 is square root 3 over 2. Cosine at pi 3rd is 1/2. Sine at pi 3rd is square root 3 over 2. And then I can combine like terms. I've got positive and negative square root 3 over 2 sine theta. Those add to 0. 1/2 plus 1/2 is just 1. So 1/2 cosine theta plus 1/2 cosine theta equals 1 cosine theta, and that was my goal. That identity is verified.